Welcome back to the explainer. Okay, let's just jump right in. If you're an AI engineer or an ML developer, you know you spend a massive amount of time working with GPUs. But let's be real, often the actual hardware feels like a bit of a black box, right? Well, instead of just accepting that, today we're going to pry that box open together. We're looking at one of the absolutely most critical, yet somehow completely misunderstood aspects of your hardware: GPU clock switching and control. We're going to break down exactly what's happening under the hood and how you can actually take the reins and control it.
Let me know if this exact scenario sounds totally familiar. You're training a model on a big GPU cluster. One day, your kernel benchmark is just blazing fast, but the very next day, it's mysteriously slower, and you haven't touched a single line of code. It's literally the identical kernel running on the exact same hardware, but the results are just different. It's incredibly frustrating, and honestly, our first instinct is usually to frantically tear through our code looking for a bug we somehow introduced, way before we ever stop to think, hey, maybe it's the hardware. So, eventually you open up your terminal to investigate. You fire up NVIDIA SMI and bam, you're immediately hit with a sheer wall of shifting numbers. You've got a graphics clock, an SM clock, a memory clock, different power states, application clocks, the whole shebang. And if you sit there and watch them while your code runs, they're just fluctuating wildly in real time. Now, it kind of looks like you have the ability to lock or tweak some of these values, but what is changing them actually due to your training speed or your inference latency? Well, here's our roadmap for today to figure that out. First, foundational domains. Second, the control mechanisms. Third, the mental model. Fourth, practical scenarios. And finally, a recap and takeaways. Let's get into it.
Starting off with Section 1, Foundational Domains, Understanding Clocks.
When we throw around the word clock in this context, we definitely aren't talking about a single overarching speed limit for your entire computer. No, we're talking about different clock domains. Think of a clock domain as just a specific part of your system that ticks at its own independent rate. Your CPU has a clock. Your GPU's streaming multiprocessors, the SMs, have their own clock. And the GPU's memory, the VRAM, has a completely separate clock. So you're never really looking at one master GPU speed. It's more like several distinct domains working together. And actually, moving the data around takes time too, not just crunching the math, which is exactly why that separate memory clock is so fundamentally important. Let's actually map these distinct domains directly to your day-to-day ML workloads. Look at the CPU domain first. That's the host side, right? It's handling the orchestration, data loading, tokenization, preprocessing. Then you've got the GPU SM or core clock. This is your math engine. It drives those tensor cores. When you run a compute-bound kernel, like a massive matrix multiplication or a fused attention kernel, this specific clock sets exactly how many floating point operations per second you can pump out. And finally, we have the GPU memory clock. This controls the bandwidth between those SMs and the VRAM. So if you've got memory-bound workloads, think handling huge models or massive batch sizes, this bandwidth literally dictates how fast you can feed data into that math engine.
But here's the catch, and it's a big one. These clocks aren't totally independent. By default, your system uses this thing called dynamic frequency scaling. Essentially, vendors define performance states, usually called P states, and they tie them strictly to power and thermal limits. The hardware will automatically boost clocks up when there's some thermal and power headroom, and then immediately throttle them back down the second you hit those physical limits. So remember that frustrating moment we talked about earlier, that slower benchmark? That is exactly why it happened. The dynamic environment changed, the hardware probably got hotter, and the system throttled itself down to compensate.
Moving on to Section 2, the control mechanisms, overriding dynamic boost.
Now, for a lot of data center GPUs, like your A100s or H100s, you can actually manually set these speeds using terminal commands. It's a pretty logical three-step progression. Step 1, you almost always need to enable persistence mode, running NVIDIA-SMI-PM1. This is absolutely crucial because it keeps the NVIDIA driver loaded even when no active apps are running on the GPU, which ensures your custom clock settings actually stick around. Step 2, you use the AC flag to set application clocks. This is where you request a specific memory and graphics clock pair within a vendor-approved range. And finally, Step 3, if you want to eliminate variance completely, you use the -lock GPU clocks flag. This forces the SM clock to stay locked strictly within a minimum and maximum range. Of course, if you're managing a massive cluster, you really don't want to be typing out terminal commands all day long. So for programmatic control, NVIDIA actually provides the NVML library. By using CAPIs like NVML device set GPU locked clocks, you can lock these speeds automatically right from within a monitoring app or an orchestration script.
Just a quick heads up, though. These commands usually require root or admin privileges, and they're typically restricted to true data center hardware. You're probably not going to be doing this on your consumer gaming laptop.
All right, Section 3, the mental model, safe versus risky control. Because here is the absolute truth of the matter. Just because you can change these clocks does not mean you should without really understanding the profound trade-offs. There's a very hard boundary here between safe and risky control. Safe clock control means locking clocks strictly within vendor-approved ranges to get rock-solid stability, guarantee reproducible benchmarking, or maybe just doing some mild underclocking to save power. Risky overclocking, on the other hand, means pushing the hardware way outside its rated spec. And doing that, it invites total disaster. You're going to generate excess heat, which causes severe thermal throttling, system crashes, and honestly, the absolute worst nightmare for ML engineers, silent data corruption. That's where your model learns absolute garbage and you don't even get an error message telling you why. No way you want to deal with that.
There's a golden rule you really need to remember here. For ML training and production, stability often matters more than that last 3% performance. I know, it is incredibly tempting to chase every single last drop of speed to get your model out faster. But just imagine a massive multi-day training run that completely crashes at 95% completion, all because you pushed the SM clock a little too high. That is a massive waste of both time and a very expensive compute budget. So don't fall for the hype. Prioritize stability above all else.
Which brings us to Section 4, Practical Scenarios, Real-World Uses.
So where does this actually show up? There are basically 3 primary scenarios where you're practically going to use clock management in your day-to-day workflow. Long-running ML training, fine-tuning your code through CUDA kernel profiling, and managing production inference services. Let's break these down real quick.
Scenario 1 is training. Look, when you're utilizing a massive cluster of data center GPUs, you want absolute consistency. By using application clocks to lock the SM and memory clocks across the entire cluster, you make your training throughput completely predictable. This makes capacity planning an absolute breeze. Plus, if you're working in a thermally constrained data center rack where things run a bit hot, mildly underclocking those GPUs can actually prevent catastrophic hardware failures during brutal multi-day runs.
Let's jump to Scenario 2, profiling. Say you're writing a custom kernel and using a tool like Nsight Compute. You really need to know if your specific code tweak actually caused a speed up or if the hardware just dynamically decided to boost on its own, right? Well, by locking your SM and memory clocks during profiling, you completely isolate your code improvements from that dynamic hardware variance. Honestly, it's the only way to get clean, repeatable measurements that actually prove your optimization worked. And Scenario 3 is inference. In production inference, flexibility is the name of the game. If your model easily meets its latency targets, you can safely underclock the GPU. Now, I know it sounds crazy to intentionally slow things down, but running hundreds of GPUs even 100 megahertz slower can save literally thousands of dollars in electricity and cooling costs at a data center scale. On the flip side, if you're hovering right on the edge of missing a super strict service level agreement latency target, a very small vendor-approved bump in the SM clock might be exactly what you need to reduce tail latency, assuming your cooling systems can handle it, for sure. And finally, Section 5, recap and takeaways, core principles.
The ultimate philosophy you should adopt when interacting with GPU hardware really boils down to these 3 core principles. First, understand your clock domains. Remember, your system isn't driven by one single speed. The CPU, SM, and VRAM all play distinct, crucial roles, depending on whether you're memory-bound or compute-bound. Second, change clocks intentionally. Overriding dynamic scaling means trading off performance, power, and stability. Don't just do it blindly. Let your profiler data guide those decisions. And third, prioritize stability. The real sweet spot for serious ML work is predictable performance, not extreme, risky overclocks.
Thank you so much for joining me today for this explainer. Now that you've got this mental model, I challenge you. Fire up your terminal, run NVIDIA SMI, and really observe what your hardware is actually doing. Because next time your kernel runs, you have to ask yourself, who is really controlling your clocks? You or the heat? See you next time.